track in the A track. We have David Strauss from Spark at Euclid. If anybody else in the back wants to come in and see the last sessions, please feel free. Welcome, David.
All right, thank you. So my name is David Strauss. I'm a data scientist / data engineer at Euclid Analytics. I'd like to take this afternoon to speak a little bit about how we use Spark to actually do a lot of the main heavy lifting for our analytics applications at Euclid Analytics. So first, I should explain what Euclid Analytics is. We're a company that is interested in measuring how people interact with brick and mortar physical retail spaces. In similar ways that Google Analytics and I guess Bizo, which just spoke a few minutes ago, actually monitors who comes to websites and how long they stay there and how often they come back. We're trying to quantify and measure those exact same things for physical retail locations. We do this by monitoring Wi-Fi devices in the area. We listen with Wi-Fi access points that are placed within stores, and we're able to assign a unique identifier to smartphones that are in the area. We log some of these devices that are in the area, send them off to a cloud storage where we do a bunch of processing, and then we present anonymous aggregated data to the retailers themselves, giving them metrics such as shopper duration, repeat visitors, and many other things that let them know and build better businesses. At our core, we're a data processing and data platform company. We process log files from Wi-Fi access points, and we use a small amount of data that we obtain about a lot of different smartphones to infer what these smartphones are doing and what they might do next. From each device, we just get simple, unique identifier, a timestamp, and signal strength. Wi-Fi is a radio transmission, and so signal strength corresponds roughly to how far away a device might be from an access point. Low signal strength would correspond to being further away than high signal strength. So we get these three fields, and we search for patterns that correspond to different types of user behavior. You might start to think about our data in something like this form, where you have on one axis signal strength, and on the other axis, the y-axis in this case, dwell time, or how long a device sticks around in a particular location. And you can start to see that in this particular contrived example, there are some very, very clear patterns. We go about labeling some of these patterns by actually seeing how certain devices behave, and we get things like this cluster of devices that has high signal strength and relatively short dwell time. Those might actually be visitors at any particular store. Devices that have low signal strength and even shorter dwell time, those might actually be people just simply walking by the front of the store. And you have other classes of devices, such as the people next door, and sometimes the staff members who stick around for much longer periods of time, presumably, than any visitor at a store. So in this particular example, it's very easy to see a lot of separation between the data, and you might think that we might want to start modeling our data using some type of mixture model. Unfortunately, when we go to look at the real data, it turns out it's a little bit messier. These clear clusters that we hope to find don't actually exist, and we need to spend much more processing power and create much richer models in order to actually understand what these devices are doing with respect to the physical locations and stores. In order to understand these raw data, we've chosen to use Spark as a way to develop many different models that can actually allow us to infer the different types of behavior that exist in the data and figure out what each device is trying to do and how that relates back to this business. We chose to use Spark for many different reasons. One of the first reasons being that it's got a very nice code integration, as well as implements really nice functional programming. These two tasks make it very easy for many different developers to collaborate to create a very scalable and easy to test method for building models and really doing a lot of the different aggregations that we need to do. Spark is a platform on which we can create a lot of scalable machine learning to really develop many different models and test a lot of different models. It's extensible, meaning we can write some core functionality and continue to add to it as the application and the data processing need permits. And last, of course, everyone knows Spark allows for in-memory caching, which means we can speed up a lot of iterative algorithms for machine learning, and it also allows very complex data flows to be very simple and fast. Not only does it allow us to use iterative algorithms for machine learning, but it actually allows our team to iterate faster on producing algorithms that can actually improve the accuracy that we have in our data processes. Some of the challenges that we faced over the last couple of months as we're bringing Spark online include being able to launch clusters regularly and reliably for all the members of the team, of our data science team. Furthermore, we've had to make sure that the pipeline that we put together is able to update and apply models and hold on to those model parameters in a really clean and user-friendly way. Furthermore, we've had to look at distributed optimization problems. We collect data on thousands of sensors worldwide every day, and we need to actually create a custom-tuned model for each one of these sensors. So we are faced with distributed optimization problems and custom models for each individual sensor. And last, we've had to make sure that everyone on the team is able to hop into Spark and be up and productive, and really do a lot of work to migrate some of our older jobs from older platforms onto Spark, so that way we can have a very unified platform. So all of our services run on Amazon Web, and we use created a lot of ad hoc clusters on a nightly basis and on a daily basis in order to do data analysis. We created other companies have, and Ouya has really come up with a nice API and a job cluster manager. We actually created a little bit of a cluster manager ourselves using a Python class. This Python class allows us to abstract a little bit of the cluster management process, spinning up clusters, turning them on, getting the right resources allocated, and then even turning them off eventually when a job is complete. And we've wrapped this in a Python cluster manager, so that way we can actually catch exceptions. If a job fails or if some other step fails, we can actually catch those exceptions and clean up in a very nice way. We were able to actually script starting a cluster and executing some remote job, say in this particular case, our com.euclidanalytics.foo job, in about 3 lines of code. And this allows us to launch the cluster, clean everything up, and do everything that we need to do in the meantime. The idea is that we want to make sure that authentication and those sort of things are left to config files, so as we move from test environments to production environments, nothing actually changes in the code itself, but just some of the environment parameters that are around it. Oftentimes, we want to have to make sure that if we've spun up a cluster, we want to make sure that it can stick around for a while, so we've also given ourselves a keep alive flag in a similar fashion to the way that EMR jobs give you a way to keep jobs alive. We've had to do a lot of work in order to make sure that our nightly computation and model update actually works in a smooth and seamless way. This is kind of a brief outline of the way that our job is structured. Our raw data comes in from some large data warehouse. This is a big data store. And the first step is to pre-process the data. As you saw from the earlier data example, a lot of our data is rather messy, and there are a lot of different dimensions and a lot of different features that we pull out in order to use for machine learning algorithms. Our pre-processing step is sort of disconnected from a lot of the other algorithms. We like to apply things like naive Bayes and Gaussian mixture models and so on and so forth to different sets of features in order to come up with the best and most accurate classifiers for what people are doing. Spark has enabled us to really take advantage of really do a lot of iterative algorithms. We have a sequence of steps by which we update a bunch of parameters in these algorithms. Say we're looking for the optimal split for a binary tree or other type of search tree, or really trying to find the exact centers of a lot of the clusters for each given sensor. We can do a lot of this sort of stuff in a very iterative and quick way. Once we've found the optimal parameters, we can actually go on and compute the classifications, and then chain together a bunch of roll-up steps that allow us to aggregate and present the final outputs of our computations in such a form that might be presented to the actual clients, actual retail stores who are looking at the data. One particular example I'd like to highlight, we do a lot of search for parameters. Like I mentioned in the last slide, we're often looking for different types of parameters that are custom tuned for each and every model, each and every sensor that we have out in the field. And so one particular algorithm that we might use is, say, a binary search for a specific parameter. We do this on a nightly basis for each one of our models in order to get the optimal split. And because we're trying to learn a model for each individual sensor, we have to actually learn about several thousand models every night and be able to apply those in a pretty unified way as well. So one of the patterns that has been developed, or you can see often in a lot of the MLlib machine learning packages, is that you have one gigantic RDD of data, as shown here. From that RDD, you're trying to learn one model, say one k-means model or one naive Bayes classifier, something like that. Essentially, you've got the data itself, you do a map, you do a reduce to get some sort of parameters that define the model. You then might do something like broadcast the parameters of that model out to the entire data set, so that way you can actually go on to the next iteration to slightly tune and tweak the model. Our use case is a little bit different. We have one RDD where all of the data is keyed by maybe sensor ID or something like that, and we want to learn one model for each individual sensor. A lot of the same steps can be applied. You still have a reduce step, you still have a map step, but we're doing a reduce by key and collecting all of those parameters as a distributed set of model parameters. We then have to do a join back to the original data, such that these data sets and model parameters actually stay as fully parallel collections throughout the entire learning process. Now, as we started developing this, we noticed that a handful of things can happen if you aren't really very careful. Sometimes using a simple for loop can actually cause a lot of problems. I don't have any specific examples right here today, but you can conceive of ways, because of Spark's lazy evaluation, you might not actually force computation of the parameters in the right sequence of events in order to actually learn viable models. So our approach is actually to use a fair amount of recursive searches. So we do a lot of our optimization routines rather than employ for loops for our sort of design pattern. We like to use recursive patterns for optimization. So here we define sort of, say, some case class of model parameters. They've got a handful of fields that you see there. And we have some sort of data, which is a big parallel collection of a lot of different records. Each one has a key. We define a function. In this particular case, we call it binary search, where we input some parameters, and we actually recurse through a bunch of different levels in order to actually continue to make decisions as to whether or not we're going to update parameters one way or the other. And we keep everything as a very parallel collection, so that way we can learn across thousands of sensors and thousands of different models across thousands of sensors in a very parallel and coordinated way. Now, this isn't necessarily perfect. There are a handful of things that we still need to tune. And one of the things that you might suspect is that a lot of the shuffle steps that are involved with these joins actually become quite cumbersome. And we're still working on trying to tune and fine-tune a lot of the processes involved there. But so far, we're actually seeing the sets of computations line up in exactly the way that we want them. At Euclid, we haven't always used Spark. Back in the early days, we started off probably with just a handful of single node, single processor jobs in Python to actually figure out what's going on. And from there, we graduated to more pig scripts. We were coordinating a lot of map-reduce jobs. But those became cumbersome fairly quickly, as many of you have probably experienced using pig scripts and other map-reduce frameworks. And we eventually went over to some more Amazon Redshift for actually holding onto the data and running a handful of simple models. Of course, the models that you can run in Amazon Redshift are relatively simple, constrained to standard SQL queries. And so we actually wanted to migrate over to Spark and Scala so we could introduce richer models to our data processing. Over the last 6 months, we've upgraded to using Scala and Spark, and now we run nightly jobs with a whole host of ETL things that allow us to figure out exactly what's going on in our data stream and present aggregated anonymous data to retailers. As we move forward, we're looking toward bringing up some streaming applications. There's some various applications that we're looking toward that might really benefit from being able to produce data in real time. So that's what I'd like to tell you guys about Spark today. Thanks for listening. And if you have any questions, feel free to contact me, and I'll take any questions if we have time.
Hello.
Hi.
So you just said that you guys wrote a cluster manager in Python.
Mm-hmm.
Was there any reason to do that and not use something like Mesos?
Well, it's sort of a trade-off of, is it worth it to take the time to spin up a lot of Mesos stuff? What's the actual demand? It turns out that we don't have really a high availability necessity for what we're doing. And a lot of the things remain independent and so on and so forth, and a lot of it's ad hoc. Not everyone needs everything all at once. So Mesos would have been a little bit overkill for our application.
Hey, nice presentation. The Spark cluster manager that you just referred to as well, the Python one that sort of deploys the cluster on Amazon, as I understand it?
That's correct. So essentially, it's kind of a wrapper around a lot of the tools that are already available in Spark. Let's say, you have that command line thing with all sorts of this, that's, and the others, and so on and so forth. And so it really just allows you to define for any given user. You can say, I'm David, so I would like the David cluster and something like that. And it'll go ahead and sort of spin up those resources for you if you want that. If the production machine has a few different credentials, you can do the same thing that way.
Is that available publicly? Are you open source?
We haven't released that yet, no,
Okay.
not yet.
I think there'd be a lot of interest in that.
Cool. Noted.
Any other questions?
Great. Thank you.